By 1917, the scientific consensus was entirely settled on one idea. Researchers looked up and saw the universe as a sealed glass bottle. The galaxies inside could drift around and interact, but the overall container was entirely static. It didn't expand and it didn't shrink. But Albert Einstein's newly published general relativity equations pointed to a severe mechanical problem. His math dictated that a static universe is physically impossible. Gravity would force everything to either crush together into a single point or push outward and expand like a balloon. Einstein was terrified of being dismissed as absurd by the academic community. To fix the mathematical discrepancy, he forced a fabricated variable into his equations called the cosmological constant. It acted as a mathematical prop, perfectly balancing the forces so his theoretical universe would sit still. Rather than follow his own math to its dynamic conclusion, the leading physicist of the era doctored his findings to fit a comfortable, accepted illusion. That illusion held until 1928. Edwin Hubble spent his nights aiming the massive telescope at the Mount Wilson Observatory toward distant, pulsing Cepheid stars to track their exact positions in the sky. He isolated the light from those stars and analyzed the frequencies. The wavelengths he measured were stretched out, pushing the color toward the red end of the spectrum. In astrophysics, this physical lengthening of light waves is called redshift. It proves the object emitting the light is actively racing away from the observer. The redshift data showed that nearly everything in the sky was moving away from us. The container wasn't static. It was expanding in every direction. When Einstein reviewed Hubble's calculations, he erased the cosmological constant from his chalkboard and publicly admitted his mistake. However, answering the question of whether the universe was moving opened a far more dangerous line of inquiry. Now, physicists had to calculate exactly how that movement would end. To find that endpoint, researchers applied standard physics. If the universe started with the massive outward explosion of the Big Bang, the collective gravitational pull of all the mass in the universe should act like a brake, naturally slowing the outward expansion over time. This line graph maps the expected trajectory of that deceleration against the actual data from modern telescopes. The expansion is not slowing down. Instead, the universe is violently accelerating upward, moving faster with every passing second. The sheer amount of energy required to override the gravitational pull of all known galaxies is mathematically immense. Astrophysicists label the invisible driver behind this rocket-like acceleration as dark energy. Calculations based on this acceleration show that dark energy currently makes up a staggering 70%. Everything, including our own solar system, is being physically dragged toward this central point at massive speeds. This leaves modern astrophysics with two opposing mechanical models. Either dark energy is pushing everything outward everywhere at once, or the massive gravity of the Great Attractor is pulling our specific neighborhood inward. The ultimate fate of reality itself rests entirely on the mathematics of this cosmic tug-of-war. Which force was stronger will determine exactly how time ends. If the dark energy model is correct, we face the big freeze. The repulsive force will overpower gravity, stretching the space between every galaxy, star, and planet infinitely apart into absolute, isolating darkness. Gas clouds will become too dispersed to form new stars. The stars currently burning will exhaust their fuel and die out. The universe will settle into a temperature near absolute zero, remaining forever as a frozen graveyard. But if the Great Attractor and the gravitational forces win, the universe faces the big crunch. The expansion will violently snap back. Galaxies will merge at high speeds, generating blinding heat and crushing all matter together. The entire cosmos will compress back into a microscopic singularity. This absolute incineration of the current universe would reset the board, potentially compressing enough energy to ignite an entirely new Big Bang. Whether stretched into eternal ice or compressed by microscopic fire, both mathematical outcomes guarantee the absolute eradication of every physical structure we can observe. Today, global space agencies use advanced satellite telemetry to track the density of the universe, desperately trying to calculate which force has the mechanical advantage. We are a fragile species sitting on a tiny rock in the suburbs of the Milky Way. Yet we have developed the mathematics and the instruments to sit in the dark and calculate exactly how the curtain will close on the universe itself.